So in the last video we derived this Bayesian equation which says the probability of parameter values theta given the data that we have, and then we applied Bayes' equation. That's basically the probability of the data conditional on theta times the probability of theta divided by the probability of the data. It's this thing over here, this conditional probability, the probability of theta, so probability for certain values of the parameters given the data, that we call the posterior distribution. Yeah, so that's the thing that we're going to be working with a lot. It is what do we know about the value of the parameters after we have seen the data. So the probability of theta after conditional on the data. Yeah, you can write this equation like this. For some particular choices of probability processes and priors, there are actually analytical expressions for this posterior. We're not going to worry about that. We're actually going to use pymc3 to calculate the posterior for us. So let's simply look at an example to get an idea of how this posterior works. So the example is based on a binomial process. I'm throwing a coin, and I'm throwing a coin up to 20 times. And after each throw with my coin, I record how many tails I've seen and how many heads I've seen. And what I'm interested in is the probability of heads with this particular coin that I have. So when I threw it once, it was head. Yeah, so I have one throw and one head. When I threw it another time, so I have thrown it twice now, I still have one head, which means I have one head and one tail. I threw it one more time, so I have thrown it 3 times now, and it turned up 2 times head, 1 times tail. When I was throwing it 4 times, I had 2 heads, 2 tails. When I threw it 5 times, I had 3 heads and 2 tails. And all the steps in between I simply leave out, yeah, for brevity. But when I'd thrown it 20 times, it turned out that I had 14 times head in this sequence. So this bit of code, there's no need for you to understand it. Basically what it does is it creates the pymc3 model. The model, of course, is a binomial model. Yeah, so if I have a probability p and the event is repeated n times, the outcome of the number of times that I find something, so in this case the number of times that I find head, that's actually a binomial distribution. So we specify the prior, which in this case is a uniform distribution between 0 and 1. And then I specify the process, the probability process, which is a binomial distribution. We generate something called a trace. Again, don't worry about it. I'm actually not going to run this code here because that will take up a bit of time in the video. So when you run this at home, this will take a couple of minutes. I mean, not like 10 minutes, but it will take some time because we have to run this 6 times for each of these 6 experiments. So I've created this list, posterior list, and it contains the posterior distribution for each of these experiments. Yeah, so there are 6 elements in posterior list, and it's a posterior distribution after my first experiment, my second experiment, etc. Yeah, so now I add to this list the uniform distribution. Yeah, so this is basically just a trick, because when I want to plot things, so let's just plot it. So what the plot does is it shows you the posterior distribution of this experiment. So in this case, in blue, is the posterior after thrown once. Here it's the experiment after I've thrown the coin twice. So in blue, it's the line which has the posterior distribution for this experiment, and then the dotted line is the experiment, or the dashed line is the posterior of the previous experiment. Yeah, so you see that this dashed line corresponds to the blue line here. This dashed line corresponds to the blue line that we have over here. Yeah, so by superimposing these two in the same graph, you can see how the posterior is moving from one experiment to the next. So basically what it means is that I first plot out of the list the experiment that I'm looking at, and I'm then plotting on top of that dashed, so line style dashed, the previous one, so I'm using -1 here. Yeah, so when I run this for the first time, so it's basically element 0 out of the list, yeah, because Python is starts indexing at 0, then the -1 is actually the last element of the list, and the last element of the list is actually the uniform distribution that I've added here. Yeah. So if you don't understand much of that, don't worry about it. It's the trick that I use to generate these 6 plots. So when I threw the coin once, I immediately saw head. So now the posterior immediately thinks that it must be very likely, so P must be very high, the probability of finding head with this coin must be pretty high. Yeah, because I threw it once, I saw head. I'm pretty sure that, of course, it's not possible anymore that P is equal to 0, so this probability here is very close to 0, because I've thrown it already and I've seen the outcome head, so the probability that P is 0 is basically 0. Now I throw it a second time, and now I see one head, one tail, and you can see that the posterior immediately starts to center around 0.5. Yeah, I've thrown it twice, I've seen both heads and tails, so the mass of this posterior is pushed back to the left, because it now becomes likely that tails is also a possibility. Yeah, so we're pushing this to the left. So it becomes now unlikely that either P is 0, which would imply that I'll never observe head. And it's also unlikely that P is equal to 1, because that would imply that I cannot see tails. Yeah, so we're being pushed here to the left. I throw once more and I see 2 times heads now. So the probability mass now is pushed again to slightly higher values of P, because I've thrown it 3 times and the most likely outcome, 2 out of 3, was actually heads. Yeah, so we're sort of moving away from P is a half towards higher values of P. But then when I threw it 4 times, I had 2 times head, 2 times tails. So we're moving again to the left and we find a distribution that is sort of centered around 0.5 again. Yeah, so when I keep on throwing this, you can see this development. And after I've thrown it 20 times, I've actually found 14 heads. Yeah, so after throwing it 20 times, I'm actually pretty sure that the probability P is centered around 0.7. Yeah, and as you can see, when you move from the left to the right here and to the second row, the densities on the vertical axis actually change. Yeah, so here it goes from 0 to 1.5, but here already to 1.75 and here to 2.0. And when I've thrown it 20 times, it actually goes all the way up to 4. Yeah, so here I'm pretty sure that the probability of throwing heads is 0.6 or higher. Yeah, so although these curves may look sort of the same, the axis here is twice as high, it goes up to 4, while this one goes up to 2. So there's much more probability mass here around 0.7 than you find over here. Yeah, so that's how you can see the posterior develop after each experiment. Yeah, when I've thrown it 20 times and I find 14 heads, the probability mass is sort of pushed well beyond 0.5. Yeah, because if it would have been a P of 0.5, I should have seen out of 20, ideally 10 heads, but of course it could have been 9 or 11 or perhaps even 8 and 12, but 14 is quite a bit higher, so you know, we're sort of moving away here from the idea that this is a fair coin. Yeah, it's actually more likely that the coin is biased and that P is around 0.7. So here what you see are the density functions. Yeah, so the total area below these functions is equal to 1. So if you would integrate this, it should be equal to 1. Another way to look at it is, of course, that I plot cumulative distribution function. So I use KDE plot, but then with cumulative equal to true. Yeah, so the cumulative one, of course, always ends up at 1. So this is the sum of the probabilities. And here, for instance, you can see that if you take a probability of 40%, and we follow it sort of like here, then basically you would say that there's a 40% probability that P is below 0.65. Yeah, if this, I mean, it's not very accurate, of course, but yeah, if you do it like this is what the curve is telling you. There's a 40% probability that the P of this coin is smaller than or equal to 0.65, say. Of course, we can be a bit more accurate doing this. So here we ask this question, what's the probability that P is bigger than 0.8? So again, if I would use the figure, I would say 0.8. Oh, sorry, should here start. Here was a probability that is bigger than 0.8. So that's round about, let's say 0.9. So the probability that's bigger than 0.8 should then be around about 10%. So if we run this, it's indeed round about 10%. Yeah, so just to explain what we're doing here. So we're looking at posterior list. -2, yeah, because the last element was the prior distribution, the uniform distribution that we added to this list, and we're interested now in the posterior distribution when we had 20 throws of the coin, so that's -2 here. So what's the probability that this is bigger than 0.8? Yeah, so in Python, when you run this, you basically get a Boolean array, which contains false if actually the posterior is smaller than 0.8, and it's true if indeed it's bigger than 0.8. And in Python, false is represented by a 0, true is represented by a 1. So what I can do is I can simply sum this list of booleans. So that will tell me how often it happens that this posterior, which refers back to the experiment when I throw the coin 20 times, when this posterior is bigger than 0.8. So I can sum these things, and I divide it, so to get a fraction or a probability, I divide it by the length of this list. Yeah, so that's the total number of observations in this list. And when you calculate this, you find that it's around 10–11%. Yeah, so when you go up here, 80, it's not very accurate what I'm doing here, but indeed it seems to be around 0.9. Yeah, so there's a 10% probability that the P of this coin, so the probability of getting heads, is actually bigger than 0.8. Yeah, so that's not very likely, the fact that it's bigger than 0.8. And already we saw, of course, that it's around 0.7 actually. That's where most of the mass is accumulated. Yeah, so this gives you an idea how what the posterior is and how it reacts to the evidence that we have in terms of throws and then the number of heads and tails.